In this video, we will use binary heaps to design the heap sort algorithm, which is a fast and space-efficient sorting algorithm. In fact, using priority queues or using binary heaps, it is not so difficult to come up with an algorithm that sorts the given array in time big O of n log n. Indeed, given an array A of size n, we do the following. First, just create an empty priority queue. Then insert all the elements from our array into our priority queue. Then extract the maximum one by one from the given array. Namely, we first extract the maximum, so this is the maximum of our array, so put it to the last position. Then extract the next maximum and put it to the left of the last position, and so on. This clearly gives us a sorted array, right? So we know that if we use binary heaps as an implementation for priority queue, then all operations work in logarithmic time. So this gives us an algorithm with the running time big O of n log n. And recall that this is asymptotically optimal for algorithms that are comparison based. And this algorithm is clearly comparison based, right? Also note that this is a natural generalization of selection sort algorithm. Recall that in selection sort algorithm we proceed as follows. Given an array, we first scan the whole array to find the maximum value. So then we pick this maximum value and swap it with the last element. Then we forget about this last element and we consider only n-1 first elements. Again, by scanning this array, we find the maximum value and we swap it with the last element in this region, and so on. So here in the heap sort algorithm, instead of finding the maximum value at each iteration naively, we use a smart data structure, namely a binary heap, right? So the only disadvantage of our current algorithm is that it uses additional space. So it uses additional space to store a priority queue, okay? So in this lesson, we will show how to avoid this disadvantage. Namely, given an array A, we will first permute its elements somehow so that the resulting array is actually a binary heap. So it satisfies a binary heap property. And then we will sort this array again just by calling extract max n times or n-1 times. Building a heap out of a given array turns out to be surprisingly simple. Namely, given an array A of size n, we do the following. We first assign the value of n to the variable size, just to indicate that we have a heap of size n. Then we do the following. For each I going down from n over 2, rounded down to 1, we just sift down the ith element. Let me explain it on a small picture. Why are we doing this? So consider the following heap that we actually, let me remind you, we do not store it explicitly. We have just an array, in this case of size 15. So this is the first node, the second one, the third one, 4, 5, 6, 7. So if we just consider the corresponding array of size 15 and imagine this complete binary tree, then the heap property might potentially be violated on many edges. However, in this tree we have 15 nodes, so we have 15 subtrees. And for these subtrees, I mean rooted at the leaves of this tree, the heap property is satisfied for an obvious reason. There are no edges in these subtrees. So the first node where the property might be violated is node number 7. So potentially there might be a problem in this subtree. To fix this problem, we just call sift down for node number 7. Okay? After this call, this small subtree must be a heap, right? Then we do the same for node number 6. After this call, there are no problems in the subtree rooted at node number 6. Then we do the same for I equal to 5 and for I equal to 4. Then we proceed to node number 3. Note that at this point everything is fine in this subtree and in this subtree. right? We already fixed everything in these two subtrees. So to satisfy the heap property is in the subtree rooted at the node 3, it is enough to call sift down for node number 3. Okay? Then we proceed to node number 2, and again, after calling sift down to node number 2, we fix the heap property in this subtree, and so on. So in this example, actually, the last thing that needs to be done is to call sift down for node number 1. When we are done with this, we are sure that what we have in array A is actually a heap. So it corresponds to a complete binary tree where the heap property is satisfied on every edge. Let me repeat slowly what have just happened. So to turn a given array into a heap, we start repairing the heap properties in larger and larger subtrees. So we start from the leaves and go to the root. Initially, so our induction base is that the heap property is satisfied at all the leaves, I mean in all subtrees rooted at the leaves, for an obvious reason. Any subtree rooted at a leaf has just one node, so the property cannot be violated, right? Then we gradually go up and we fix the heap property by sifting down the current vertex. And finally, when we reach a root, the property is satisfied in the wall subtree, right? So this is just a link for an online visualization. You can download the slides and play with this visualization if something is unclear to you in this process. Let me now mention that the running time of this procedure is n log n, again for an obvious reason. So we use a binary max heap to implement the sift down procedure. So we call sift down roughly n over 2 times, and each call is just log n, right? So we have n log n running time. We already have everything to present the in-place heap sort algorithm. Given an array A of size n, we first build heap out of it. Namely, we permute its elements so that the resulting array corresponds to a complete binary tree which satisfies the heap property on every edge. So we do this just by calling build heap procedure. In particular, this build heap procedure assigns the value n to the variable size. Then we repeat the following process n-1 times. So we first recall that just after calling to build heap, the first element of our array is the maximum element, right? So we would like to put it to the last position of our array. So we just swap a1 with a of n, and currently a of n is equal to a of size. Okay, so we swap it, then we forget about the last element, so we decrease size by 1. So we say that now our heap occupies the first n-1 elements. And since we swapped the last element with the first element, we potentially need to sift down the first element. So we just call sift down for the element number 1. And we proceed in a similar fashion. I mean, now the heap occupies n-1, the first n-1 positions, so the largest element among the first n-1 element is the first element, so we swap it with element number n-1. We forget about the element n-1 by reducing the size by 1, and then we sift down the first element. Okay, so we repeat this procedure n-1 times, each time finding the currently largest element. So once again, this is an improvement of a selection sort algorithm, and this is an in-place algorithm. So once again, let me state some properties of the resulting algorithm, which is called heap sort. It is in place. It doesn't need any additional memory. Everything is happening inside the given array A. So this is an advantage of this algorithm. Another advantage is that its running time is n log n. It is asymptotically optimal. So this makes it a good alternative to the quick sort algorithm. So in practice, quick sort is usually faster. It is still faster. However, the heap sort algorithm has worst case running time n log n, while the quick sort algorithm has average case running time n log n. For this reason, a popular approach in practice is the following. It is called intra-sort algorithm. You first run quick sort algorithm. If it turns out to be slow, I mean, if the recursion depth exceeds c log n for some constant c, then you stop the current call to quick sort algorithm and switch to heap sort algorithm, which is guaranteed to have running time n log n. So in this case, in this implementation, your algorithm usually, in most cases, it works like quick sort algorithm. And even in these unfortunate cases where it works in larger, where quick sort has running time larger than n log n, you stop it at the right point of time and switch to heap sort. So this gives you an algorithm which in many cases behaves like quick sort algorithm, and it has worst case running time at most big O of n log n.